In this video, I'm going to talk you through Topic 4, Atomic Structure of the AQA Physics GCSE specification. The first part that we're going to look at in this unit is called the development of the atom. So when we started thinking about development of the atom, we start with John Dalton, who was the first scientist credited with thinking about the atom. Dalton claimed that atoms couldn't be divided or split into different parts. But this idea or this theory changed when J.J. Thomson discovered the electron, and then he created a new model which he called the plum pudding model. The plum pudding model is shown on this side over here, and basically what it was is he thought of the atoms to be like a plum pudding. So you'd have the plums dotted around inside the pudding. The plums were the electrons, so they had negative charges, and the pudding itself was a positively charged gas. And that was the theory that we used to use with the atom about 100 years ago. With all good theories, this needed to be tested and stand up to scientific evidence. So Rutherford designed an alpha particle scattering experiment, which he got his two understudies to carry out, and they were Geiger and Marsden. Basically, they used alpha particles to test the plum pudding model. Unfortunately for the plum pudding model, it didn't stand up to that test. The predictions that the plum pudding model made was that the particles would pass straight through. The observations that were carried out through the experiment showed that this wasn't the case, and that meant the plum pudding model was incorrect, and Rutherford then went on to create a new model called the nuclear model of the atom. This nuclear model of the atom that Rutherford proposed was further adapted by other scientists throughout the years. The first person to add some adaptations to this was Bohr. So he added that the electrons would orbit the nucleus at specific distances or energy levels or shells, and that allowed us to then add electron shells to our atomic model, our nuclear model. Later scientists discovered things like protons, which came into part of the nucleus, and then James Chadwick's experimental work showed the existence of neutrons, which were also present in the nucleus. And that brings us up to the model of the atom that we teach you now. So it's worth looking in more detail at the Rutherford scattering experiment. So we use an alpha particle, as shown here, which is a helium nucleus, so it just contains 2 protons and 2 neutrons, and has a positive charge. The alpha particles were fired at a thin gold foil, and we can see what happened to the alpha particles as they came through. So the first observation, as you can see here and here, is that most of the atoms pass straight through and would not deflect at all. And what Rutherford did is he explained that observation by saying that most of the atom is empty space, thus allowing the alpha particles to pass straight through. The second observation was that some atoms that got quite close to the nucleus but didn't directly hit it were deflected, and they were deflected through small angles. So some were deflected through small angles, and how Rutherford explained that is that there's part of the atom which has a strong charge, or a powerful charge, causing that to be deflected. He couldn't say whether it's positive or negative because he didn't know whether it was being attracted or repelled. The third and final observation that Rutherford and his team made was that about 1 in 10,000 particles were deflected by an angle of more than 90 degrees. So you can see here, it comes in, if it was going to have a direct hit with the nucleus, it would then be deflected by more than 90 degrees. And how Rutherford explained that is he said there's a small central part of the atom which contains most of the atom's mass. And those 3 observations allowed Rutherford to develop his model of the atom, the nuclear model, that then was added to the point where we have the representation or the model that we use today. So here is the structure of the atom and the model of the atom that we use today. It consists of 3 particles: the proton, the neutron, and the electron. Those are the 3 particles that make up the atom. They have different relative masses and different relative charges. We compare the masses and charges to the proton. So the proton has a relative mass of 1. It has a charge of +1. When we compare the neutron to the proton, they're about the same size, the same mass. So they both have a relative mass of 1. But the electrons are much smaller. They're about 2,000 times smaller. So the mass of an electron is 1 over 2,000. The neutrons, hence from the name neutron, is neutral, so it's 0 charge, and the electrons have negative charges. Where they are positioned in the atom varies, so the proton and the neutron are found in the nucleus, and then the centre of the atom, and the electrons orbit around the nucleus in electron shells or electron orbits or energy levels, and that is the model of the atom that we use now. As part of atomic physics, we also need to be aware of isotopes and ions. So an isotope is shown here. We've got 2 versions of carbon here, carbon-14, and carbon-12. Carbon-12 is the stable form of carbon, and carbon-14 is a radioactive isotope. You can tell then that the mass number here is different, but the proton number is the same. So an isotope is an atom of the same element with the same number of protons, and that usually gets you the first mark in the exam, but a different number of neutrons, which would get you the second mark. The next variation of atoms that we need to be aware of are what ions are. So ions are atoms that have lost or gained an electron. This causes the ions to have an overall charge. So you can see that if we were to add an electron to our helium nucleus, so we've got 2 protons, 2 neutrons, means it's a helium nucleus. We've now added an electron, so we'll have 3 electrons, 1, 2, 3. So we've got 3 minuses and only 2 pluses, which means that this ion has an overall charge of -1. If we were to lose an electron, as shown down here, again this is a helium atom, so we've got 2 neutrons, 2 protons. This time we've got 1 electron in the outer shell because we've lost an electron. That means we've got a +2 from the protons and a -1 from the electrons, giving an overall charge of +1. And that explains the difference between isotopes and ions. So ions are usually caused when ionizing radiation is incident on an atom, and that causes electrons to be removed. Another part of the course that you need to know is you need to know how atoms emit light. So what happens when an atom emits light is you basically got these orbital electrons that orbit the nucleus in their electron shells or energy levels, and they can gain energy. They can gain energy from either incoming electrons, being heated, or absorbing ionizing radiation. That could cause the atoms become ionized, so it could lose the electron, or if the energy is not great enough, it can cause the atoms to become excited. And what that means is the electron will move to a higher energy level. So here's our helium in its ground state. What we've got here is this electron's been excited, so it's gained energy, and it's moved up an energy level, or it's moved on to the next electron shell. As you know, electrons don't really like being on the energy level above the ground state. So what will happen after some time, the electron will move back down to its original energy level. We call that de-excitation. So as the electron is going from a higher to a lower energy level, it will emit an electromagnetic wave. Basically, it's losing energy, and as you know, energy needs to be conserved, so you can't just get rid of that energy, it has to emit it somehow. So as an electron moves from a higher to a lower energy level, as shown here, it will emit that excess energy as an electromagnetic wave. And that is how atoms emit light, because light is a form of electromagnetic radiation, but also they can emit things at other parts of the electromagnetic spectrum, such as UV or X-rays or gamma rays. The energy of the electromagnetic wave is equal to the difference in energy between the 2 energy levels. So as an electron moves down, it will go from one energy level to the next energy level. Those 2 energy levels have a set value for energy, and the difference between them is the same energy as the electromagnetic wave. When you look at a periodic table, you see the elements shown in the form that's shown here with carbon-12. So you can see that we've got the top number is 12, the bottom number is 6, and we've got the symbol C, which tells us it's carbon. You need to be aware of what these two values are called. So we've got the atomic mass number, or the mass number which is 12, and that is the total number of protons and neutrons combined. The bottom number, 6, here is the atomic number of an atom, and that's the number of protons, which for all atoms is the same as the number of electrons. You can then use this, or you're expected to be able to use this, to work out the number of protons, neutrons, and electrons within that atom. So because this number at the bottom is 6, that tells us we've got 6 protons. To work out the number of neutrons, we have to take use the mass number and subtract from the mass number the atomic number. So you do 12 minus 6 to get 6 in this case. And then finally, the number of electrons is just the same as the number of protons. We can now apply this to the other isotope of carbon, so carbon-14. Remember, we've got another isotope here. So if we do the same process again, we start off with the bottom number, the atomic number, we can see we've got 6, so we've got 6 protons. We're then going to work out the number of neutrons by doing the mass number, which is the top number, 14, take away the bottom number, which is the atomic number, which is in this case is 6. So we do 14 minus 6 to get 8. And then because it's an atom, the number of electrons is also going to be 6. Now I'm going to look at the types of nuclear radiation. So there are 3 main types of nuclear radiation, and they're alpha, beta, and gamma. So the first one we're going to look at is alpha, which is up here. So alpha particles occur when an atom decays into a new atom and emits an alpha particle. An alpha particle, remember, is a helium nucleus, so it contains 2 protons and 2 neutrons. Remember that you'll have a charge of +2 because there are no electrons there. So you have a start off with an unstable nucleus that's quite high in mass. It will decay into a new nucleus by emitting an alpha particle, which is a helium nucleus. Next we're going to look at beta particles. To decay through a beta particle, what has to happen inside the nucleus is that a neutron turns into a proton. So within the nucleus here, a neutron is going to turn into a proton, and that process is going to release a beta particle, which is a high energy electron. The high energy electron is released to make sure the charge is balanced, because you're adding a positive charge with a proton as the neutron changes, and therefore you need a negative charge to make a neutral overall. The electron that's emitted from the nucleus of the atom is not from one of the shells, it's from the actual nucleus itself. It's a fast moving high energy electron, and we call that the beta particle. The third type of radiation that we're going to look at is gamma rays. Okay, gamma rays are usually emitted after alpha or beta decay, and what happens after alpha or beta decay is the nucleus is often left in an excited state. As it's in an excited state, it will basically need to lose some excess energy, and it loses that excess energy as a gamma radiation or a gamma wave. Remember that gamma radiation is very high frequency, very short wavelength, and it's part of the electromagnetic spectrum. Nothing in terms of nucleus is changed when gamma is released. So you can see here, actually what we get is an unstable nucleus decays through alpha in this case. So the alpha particle disappears, leaving a new nucleus behind, and then after some time, the new nucleus will decay into from its excited state by emitting a gamma ray. You're also expected to know from the AQA syllabus that there's a fourth type of nuclear radiation, or a fourth way that atoms can decay, and that's through emitting a neutron. And remember that a neutron is just part of the nucleus, and some atoms become more stable will emit a neutron. Increases. So now I'm going to look at some of the radiation in more detail. So we'll start off with alpha again. So alpha radiation is a helium nucleus, we've already said. It has a relative charge of +2, because remember a helium nucleus has got 2 protons, 2 neutrons, but no electrons. So 2 protons have a charge of +2. There's no electrons to balance them out, so you have a charge of +2. The relative mass is 4, because you've got 4 nucleons, 2 protons, 2 neutrons, makes 4. So it's relatively big compared to the other forms of radiation. It's stopped by paper, so it doesn't penetrate very far. It only travels a few centimetres in air. But it is the most ionising, which means that it will turn atoms into ions more frequently than the others. The fact it's most ionising means that it doesn't get very far because its energy is absorbed as it ionises atoms that it collides with. The next type of radiation we're going to look at is beta. So remember that beta is a high energy electron that's emitted when a neutron turns into a proton. Because this electron has a relative charge of -1, its relative mass is small, 1/2000, but it's still got mass. Beta particles are stopped by aluminium, okay, and it's got a medium ionisation power. Beta particles can travel about a few centimetres to a few metres in air. We're going to look at gamma next. Remember that gamma is an electromagnetic wave. It has a charge of 0 and a mass of 0. It doesn't have any mass at all. Remember that beta is very small, but it still has mass, whereas gamma has no mass. To stop gamma, you need quite a lot of different things, and even lead and concrete don't absorb it completely. It's still got quite a lot of energy, so you can get through those. So it's very difficult to stop. It's very penetrating and can travel a few kilometres. And it obeys the inverse square law, which obviously the further away you are from the substance that's radioactive, the less of the gamma radiation that will reach you. It's the least ionising though. If we're going to add the neutrons to this table, remember that a neutron is just a neutron, so it's part of the atom, part of the nucleus. It would have a relative charge of 0 because it's a neutron and neutral. It'd have a relative mass of 1 because it's a neutron and they have a relative mass of 1. To stop a neutron, you kind of need hydrogen-rich things such as water, concrete, or you can sometimes use boron inside like nuclear reactors. In terms of ionisation, a neutron is not ionising directly. However, if it's absorbed by other atoms, it will cause them to decay, and that can lead to ionisation. We're now going to look at the decay equations for alpha and beta. So we're going to start off with alpha. So remember, when something decays through alpha, it emits a helium nucleus. There's a symbol we need to use for alpha, He. And remember that a helium nucleus has an atomic number of 2, because it's got 2 protons, and a mass number of 4, because it's got 2 protons and 2 neutrons. So if an atom was to decay by alpha, the nucleus that's left at the end, the stable nucleus that's left at the end, would have 4 less protons and neutrons, so 4 less nucleons, and 2 less protons. So what would happen to its atomic number is it would go down by 2, and its mass number would go down by 4. So to see that example then, we've got radon here, which you've got 219 and 86. When that decays by alpha, with 2 and 4, what happens is that the atomic number goes down by 2, so we get left with 84 for polonium, and we get its atomic number going down by 4, and we're left with 215. And if you look across here, so 215 add 4 gives you 219, and 84 plus 2 gives you 86. So those balance on either side of the arrow. And if you're asked to do a decay equation, that's something you should always check at the end. Is this number here equal to that number and that number? So if we were to look at beta now, what happens when beta decays, remember, is that inside the nucleus, a neutron turns into a proton and an electron is emitted. So you can see here that this is the symbol for beta, the E for the electron. You've got a -1 here and a 0. So if a proton turns into a neutron, well, the number of nucleons, or the number of protons and neutrons, stays the same, but the proton number increases to show that 1 neutron has turned into a proton. So if we had our original element over here, which is X with Z and A, the nucleus it decays into, once beta has been emitted, is going to have just 1 extra proton. That's what we need to add. So we can see an example for that with carbon-14 here. So carbon-14 contains 6 protons, 14 nucleons, which is protons and neutrons, remember. So as that decays, the nucleon number stays the same, 14, but the atomic number increases by 1. So you can see that's gone up to 7 from 6, making it now nitrogen. And again, if you check the tops and the bottoms to make sure they balance, you've got 14 on this side here. On this side, we've got 14 plus 0, which gives you 14. And if you look at the bottom number this time, the atomic number, we can see we've got 6 for carbon. That goes to 7 plus -1, so 7 minus 1 is 6. And again, that's balanced. So now I thought it would just be worth going through some key terms for radioactivity. So the key thing about radioactivity is that some atomic nuclei are unstable. So to become stable, the nucleus gives out radiation as it changes to become more stable. And that's a random process, and we call that radioactive decay. Now it's really important that you understand that radioactive decay is a random process. You can't predict when it will happen, because it just happens randomly within the substances that are radioactive. We can measure something called activity, which is a rate at which a source of unstable nuclei decays, and we measure activity in becquerels, which has the symbol BQ. We also can measure radioactivity in terms of count rate, and count rate is the number of decays recorded each second by a detector. So we can measure count rate using something like a Geiger-Müller tube, which you've probably seen in demonstrations on detecting radiation. Now, I've mentioned before that radioactive decay is a random process, so it's very difficult to tell when an individual atom will decay. However, for a big sample of atoms, we can quite accurately predict how many of them will be left after a certain time based on the half-life. So half-life of a radioactive isotope is the time it takes for the number of nuclei of that isotope to have halved, or the time it takes for the count rate or activity from a sample to contain the isotope to fall to half its initial level. You could be asked to determine the half-life from a graph as shown here. So what you would do there is, if you imagine that we've got numbers on this side, so we're starting off, say, at 100 at the top, you'd follow it down to halfway, which is at 50 here. You'd read across and go down, and that time that you read off the axis here is equal to the half-life. So remember that the half-life is the time taken for the count rate or activity to decrease to half its initial value. That stays the same regardless of how much or how little of the radioactive substance you've got left. So you can see we went from 50 to 25 and read across, the value we'd have got between here and here would have been the same amount of time. We're now going to look at 2 more key terms, contamination and irradiation. So radioactive contamination is the unwanted presence of materials containing radioactive materials in other objects or organisms. So contamination is when the radiation is actually inside the substance. So here we got a diagram that tries to illustrate that, is the radiation will be inside and the radiation is coming from within that material. We can use contamination in medicine by the use of radioactive tracers. So how radioactive tracers work is they allow us to map internal organs. So you would get the patient to basically consume some radioactive material that will be attached to an isotope that's designed to go to a specific organ. When it goes to that organ, it will emit the radiation from that organ, and that will then be detected using something like a CT scanner, and a 3D image of that organ will be able to be built up. Irradiation is the other key term you need to know, and that's the process of exposing an object or organism to nuclear radiation. The key thing to remember here for irradiation is the object or person does not become radioactive. So irradiation is shown by this diagram, where the radiation is outside the substance and it's travelling into it. Again, irradiation can be used in medicine, in radiotherapy, and that's basically where you use radiation. You irradiate the patient that maybe is suffering from cancer or something, and the radiation will kill the cancer cells, but do remember the negative consequences that it also kills the healthy cells around it. So that brings us to the end of the combined content now. So if you're on the combined AQA pathway, you can stop listening because we've covered all the content for your exam. If you're doing the triple pathway for AQA, I suggest you continue listening to the video to find out the triple only content. Just a further reminder for those of you doing the combined science pathway, you can turn the video off at this point now. Okay, so the first slide on the triple only content is about background radiation. Background radiation is around us all the time, and it comes from a few different places. So natural sources such as rocks and cosmic rays from space. You also get it from man-made sources such as the fallout from nuclear weapons testing and nuclear accidents. The level of background radiation and radiation dose may be affected by occupation and or location. So within the UK, Cornwall is slightly more radioactive than other parts of England, and across the world there are other areas in the world that are more radioactive than other places. And that's just down to the rocks and the region that you've got there. In terms of occupations, obviously if you work in a nuclear power station, or if you work constantly with nuclear sources, you're going to have a higher radiation dose. But also if you're a pilot, you're not being as protected as much from the atmosphere, so you'd have an increased radiation dose compared to other people. Most of the background radiation then comes from radon gas, which is just sort of in the air and it comes from the ground. We get a small proportion from our food and drink. About 10% comes from cosmic rays, and we also get 14% coming from gamma rays and the grounds of buildings. Only 15% of the radiation we're exposed to really comes from artificial sources, and that tends to be mainly from medical, nuclear discharges, products, fallout, or occupational. So you can see it's a very small amount that we actually receive from artificial sources. The last thing to talk about is radiation dose. We measure radiation dose, which is how much radiation we're exposed to, in sieverts, with the symbol SV. We tend to measure it in millisieverts, and you need to know that there's 1,000 millisieverts in 1 sievert. So now I'm going to look at nuclear fission. So nuclear fission is when a large nucleus splits into 2 smaller nuclei, releasing 2 to 3 neutrons and energy. Spontaneous nuclear fission occurs naturally, but is very, very rare. So most of nuclear fission that we see has to be induced. Now, induced nuclear fission involves firing a neutron into a nucleus. We tend to use uranium-235 or plutonium-239 in power stations and atomic warheads. And what happens then is once you fire a neutron into the nucleus, it becomes unstable. As it becomes unstable, it splits into 2 smaller nuclei, usually barium and krypton, and then that would release energy and 3 or 2 neutrons. Now those 3 or 2 neutrons will then go on and create nuclear reactions themselves, because they'll go on and collide with other nuclei that will then decay. So you can see here the effect of what we call a chain reaction. So each fission reaction releases neutrons that are used to start further reactions. So you start off with 1 neutron striking a nucleus, that becomes unstable and splits again into barium and krypton, releasing energy. We then get 3 neutrons out. They all start their own interaction, which splits again, releasing energy, and we get 3 neutrons out of each of those, and that process would continue and continue. Now in a nuclear bomb, that process is just allowed to go on. It's uncontrolled. It just happens, it starts and it goes. And there's no containing it afterwards. Whereas in a nuclear power station, what we need to do is we need to keep that controlled. And the way we do that is by the use of controlling these neutrons. So we have things like boron control rods that we can insert into the nuclear reactor, which absorbs excess neutrons and reduces the reaction. They also use a moderator to slow these neutrons down to make the reaction more efficient. The other thing that happens in nuclear power stations is you've got something called a coolant that takes the heat away from the nuclear reactor, takes that to the heat exchanger, where it's used to heat up water, which boils, turns to steam. The steam will then drive a turbine, the turbine drives a generator, and the generator produces electricity, and that's how nuclear power stations work. You also need to know that nuclear power stations tend to be encased in concrete to stop harmful radiation from getting outside. So the final part that we need to look at now is nuclear fusion. Nuclear fusion naturally occurs in stars. It's very difficult to achieve on Earth because you need something as hot as a star inside a lab, but we're getting closer to making that happen. In terms of the things that you need to be aware about for nuclear fusion, is you start off with two small nuclei, and they join together to form a larger nucleus, and in the process release energy. So here what we've got in terms of the process, you start off with two forms of hydrogen, because they both contain one proton. So here you've got a heavy form of hydrogen called deuterium, and another form of hydrogen called tritium. They join together to form fusion, which releases energy, and on the other side they make the larger nucleus helium, where you see two protons, two neutrons, and that process releases energy. And remember that's using stars, so we will probably look at this again when you do topic 8 of space physics. I'd just like to thank you for listening to my presentation, and I hope you found it useful.